Good afternoon, this is Schweitzer, and it's a little video on properties of liquids. It's going to be a relatively short video. Um, a lot of this information is already being covered. So, first property that we're going to kind of look at here is dissolving. Obviously, one of the main properties that liquids have is they can dissolve things. So we want to make sure that we understand this property. We'll just kind of repeat a little bit. So liquids can dissolve things. Why do things dissolve in liquids? And you'd really want to make sure that you are, grab the right pen here, that you understand that you're referencing, when something dissolves, that you're referencing the attraction between the solute and the solvent. That's everything, okay? Now, what intermediary forces would be involved here? Well, it could be any of them really, but probably the most common one here is going to be an ion dipole. Now, this is dealing with things that are dipole, things that are in fact ionic. So that only works for things that are ionic compounds, and there's a good picture of it located right here. So it could be any of the other intermolecular forces, dipole, dipole, or could be hydrogen bonding. But this is not, it's not that that's wrong, it's just it's not super common for what they're trying to achieve here. So another example, okay, we're looking to write out a dissolving equation of aluminum iodide. So now we've already done this sort of stuff, but Al(I)3 dissolves to form Al plus 3 plus I negative 3. Go ahead and balance negative 1. Go ahead and balance this right away, and there you go. A couple of ways in which they would demonstrate this material on A/B test is to have you write just to show it dissolved. Of course, we'd have 1 Al for every 3 aluminums, and the aluminum would be much larger, the iodide would be much larger than, let's say, the would be a -1 charge. It's just the nucleus I was drawing there, but the iodide ion, it's got several more energy levels than does the aluminum. So you'd want to make sure that you have just Al plus 3, and then you'd have 3 I negatives. This is usually done by picking out of a picture. So understand the ratios, how they present themselves around separated, and the sizes are sometimes common things that are measured here. All right, so here we have another option here where we have a water molecule, and the iodides are negative, so we might list this guy here as the I negative 1, and then we have, let's say, the positive would be the Al plus 3. So we'd have a 1 positive here, and we have 3 negatives over here, just because that's the proportion that they were used, the ratio they're used at. So I put a little key here that this represents the I negative. Draw out 2 particle models, and we did particle models. We just did that. All right. Another thing that is important is what are the factors affecting solubility? Now, internal factors would be the intermolecular forces. What are external factors? So we have temperature and we have pressure. So in this situation, keep in mind that we could have a solid dissolved in a liquid or gas dissolved in a liquid. Now, when a solid dissolves in a liquid, temperature definitely has an effect. Increasing temperature generally increases solubility. Gases, on the other hand, when you increase the temperature, you decrease solubility. Why is this? You're going to have a hard time finding some reason why. And they're never typically asking you reasons why. They might say, under what conditions would this be the most soluble? And they'll give temperatures and they'll give pressures and things of this nature. Be aware, though, that higher pressures are more soluble for gases, higher temperatures is more soluble for liquids. So higher temperatures less soluble for gases, higher temperatures more soluble for solids. So another example here would be for solids and pressure. That's literally referring to the atmospheric pressure pushing down on this thing. So solids solubility relative to atmospheric pressure really does not appear to have a whole lot of minimal effect. Nothing that we would be too worried about. I will, however, say that as pressure increases, then generally, yes, the solubility increases. So a good example would be that of like a can of soda. You have a can of soda, you have a liquid in here, and there's lots of gases dissolved in that particular liquid, way more than ever would be ready, because there is a huge pressure above this. And when they add the pressure above it, essentially stuff enters the solution and then returns back and becomes some new balance of pressure and concentration inside the liquid. As soon as we open that container, all those gases come out, and we end up with this new liquid. If you give it a little time, it'll return pretty quickly, where the concentration of the gas in the liquid's much lower, probably quite similar to that concentration which is present in the air normally. So stuff will exit the container, and then stuff will eventually re-enter, and comes to a new equilibrium between the atmosphere and what's in the liquid. All right, so this here is just kind of a generalization of that concept we just mentioned. All right, now here's a sample question. So 50 degrees Celsius at 50 C, a 50 gram sample of ammonium chloride is added to a 100 milliliter sample of water and stirred. So this is a really important graph here. We call this, basically a solubility curve. It's something that you should be able to look at and judge and kind of figure out. Any real graph like this you should kind of be able to look at. But this is saying at 50 degrees Celsius, ammonium chloride can dissolve 50 grams of stuff. So at 50 grams, it looks like that's right on with what would be recommended for the maximum that can dissolve in 100 grams of water. So it says a couple things about the solution. That the solution will conduct electricity. My answer is yes. It's going to dissolve to produce NH4 plus ions and Cl minus ions, and those ions will allow us to be a conductor, to conduct electricity, be an electrolyte. This solution has a concentration of NH4 less than 1 molar. Well, let's see what we got here. We're going to dissolve 50 grams, all right, 50 grams, and that is per 100 grams of water, which equals, all right, this would be, let's convert this guy over to moles, all right, and it weighs 53, so it's approximately really close to 1 mole. It is a little less than 1 mole, but not much. And 100 grams density of water is pretty close to being 100 milliliters, which is 0.1 liters, which means my molarity is going to be around 10 moles per liter. So less than 1 would be a no. So 1 only. And that's just an example of some stuff involving concentrations. This is actually coming. This might be a little bit ahead of where we're at right now as far as molarity is concerned. So heads up on that. And that ends our presentation. Thank you very much.